So, hey folks, welcome to Tampa Bay Enterprise AI Community's inaugural meetup. So, I'm David Lapsley, and tonight we're going to tackle one of the biggest challenges in enterprise AI, getting from a working proof of concept to a production system. Uh, so, let me start with a statistic that should concern all of us. Why do 87% of AI projects never make it to production? So here's what surprised me when I researched this. It's not technical failure. It's not that models don't work. It's not that algorithms are wrong. The science works. The reason why 87% fail is because of three things: infrastructure complexity you didn't plan for, compliance requirements that appeared after the POC was approved, and costs that exploded from $5,000 a month to $200,000 a month, or from $43,000 to $57,000 per model per month when you factor in real GPU prices. Tonight, we're going to understand why this happens and how to avoid becoming part of that 87%. But first, let's make sure we're all talking about the same thing. So what do we mean by enterprise AI? So let's take a quick level set there. We're talking about four broad categories of use cases. So predictive, where you're forecasting demand, predicting which customers will churn, when equipment will fail. Generative, which is the hot new category, automating document creation, code assistants like GitHub Copilot, Claude Code, content generation. Analytical, where you're finding anomalies in data, assessing risk, and detecting fraud. And conversational, where AI-powered customer service, internal support chatbots, knowledge retrieval systems, and so on. But having a use case isn't enough. What really makes it enterprise? So here's what separates enterprise from consumer AI. Four things make it enterprise. Scale. You're not serving 10 users, you're serving hundreds or thousands. It needs to be available 24/7, and you're processing terabytes or petabytes of data, not gigabytes. Compliance. HIPAA if you're in healthcare, SOX if you're financial services, GDPR if you touch EU citizens. Every industry has regulations, and they all apply to your AI. Integration. So this isn't a greenfield project. You have legacy systems that are built in the 90s. You have existing workflows that people depend on. You have data governance frameworks that took years to establish. Accountability. When the AI makes a decision, someone needs to be able to explain why. You need audit trails. You need human oversight. You can't just say the algorithm said so. And this is why infrastructure matters. So here's the reality check. Public AI services like using ChatGPT mean your data is on shared infrastructure. You have no control over where it goes, how it's used, or who else is on the infrastructure. No customization for your specific needs, best effort performance. If it's slow or down, you wait, and there's limited compliance guarantees. You pay per API call, and you have unpredictable costs. Enterprise AI deployment is fundamentally different. You have dedicated or isolated infrastructure. Your data stays in your control, on premises or in your private cloud. It's fully customizable for your specific models, your specific workloads. It's SLA driven, so typically more than 99.9% uptime and guaranteed response times. It's compliance certified, HIPAA, SOX, GDPR, whatever your industry requires. And it has predictable costs. You own or lease the infrastructure, you know what you're paying. And this is why infrastructure matters. You're not just running models, you're deploying production systems with enterprise requirements. And this is what we're going to focus on tonight. So first, a bit about me. So I'm David Lapsley. I've spent the last 25 years building networking and advanced infrastructure platforms, the last 14 years focused on production infrastructure at scale, and the last 3 years on AI infrastructure in particular. I'm currently the CTO at Actualize AI, where we're tackling the infrastructure problems that kill 87% of AI projects. And that statistic isn't theoretical, it's real. And tonight I'm going to show you exactly why it happens and how to avoid it. So my background, at AWS, I was director of the Network Fabric Controllers team. We were part of the team that built the largest network fabric in Amazon's history. Currently over 100 data centers supporting AI and ML workloads at massive scale. And when you operate infrastructure at that level, you learn what breaks, what costs real money, and what actually works in production. Before AWS, I was a director at Cisco, leading the DNA Center maglev platform. That's the Kubernetes-based infrastructure that powered a billion-dollar product and supported over 800 engineers. And this is where I learned how to build platforms that scale. Earlier, I was at a company called MetaCloud, where I was VP of Engineering, building private OpenStack cloud as a service and taking that company through acquisition by Cisco. And here's what I've learned working with world-class teams at AWS and Cisco, and that is how to build infrastructure platforms that scale, how to manage infrastructure that supports millions of workloads, how to design systems that don't break when you go from 10 users to 10,000 users. And that's what we're bringing to Actualize AI. Battle-tested patterns from AWS and Cisco applied to AI infrastructure, not theory, but production systems that work. So tonight we're going to do this in two parts. So part one is strategic, and for everybody in the room, we'll talk about why projects fail, what the real challenges are, and how to make smart decisions. And this is the context that executives need and that practitioners want. In part two, I'll get more technical. We'll dive into Kubernetes, GPU allocation, ML pipelines, and multi-tenancy. Engineers will get hands-on knowledge, and executives will understand what their teams are building. And then I'll open it up for a Q&A. So let's start with the strategic view. So this is where we'll understand why infrastructure decisions matter and what you need to think about before writing a single line of code. So every enterprise AI team faces what I call the impossible choice. So option A, you can use cloud AI services. You can be up and running in days. Everything's managed for you. You get the latest models, but your data leaves your control and you can't customize as much as you want, and you're locked into a vendor. With option B, you build on premises, you have complete control, you meet every compliance requirement, and your data never leaves your data center, but it takes 18 months or more to get to production. You have to build everything yourself, and you own all the ongoing maintenance. Most organizations will look at these options and feel stuck. You either sacrifice control for speed or sacrifice speed for control. So let's go deeper into that 87% statistic. And by the way, this isn't from one source. There are multiple independent studies that confirm the same pattern. So VentureBeat in 2019, 87% of data science projects never reach production. MIT Media Lab just released a 2025 study. 95% of generative AI pilots fail to achieve measurable business impact. Capgemini in 2023, 88% of AI pilots failed to reach production. And Gartner in 2019 cite a failure rate of 85%. So this is consistent across years and sources. And if you look at Algorithmia's State of Enterprise ML survey, it breaks down why they fail. So 42% cite infrastructure complexity as the primary challenge. They didn't plan for the operational complexity of running models at scale. 31%, excuse me, hit regulatory or compliance roadblocks that appeared after the POC was approved. 28% couldn't manage the cost unpredictability. What worked in development exploded in production. And 26% struggled with data governance, getting access to the right data with the right permissions at the right time. Notice that these aren't technical failures. The models work, the algorithms are fine, but the infrastructure and governance weren't ready. Let me show you what this looks like in practice. So here's the gap in visual form. So POC versus production requirements. Your data scientist built the POC on a laptop or with a single GPU in the cloud. Production needs a GPU cluster or proper cloud infrastructure. They used a simple data set. Production needs access to all the data with proper governance. POC had best effort latency. If it took 5 seconds, that was fine. Production has an SLA, 200 millisecond response time, 99.9% uptime. Only the developer had access to the POC. Production serves multiple teams, hundreds of users with proper access control. A POC might have no audit trail. For production, you need complete audit logging for debugging, compliance, and accountability. Model updates in a POC are often ad hoc. Production demands a robust CI/CD pipeline and versioning for reliability and rollback. A POC typically bypasses compliance reviews. Production requires strict adherence to regulations like HIPAA, SOX, or GDPR. Finally, a POC usually has no cost monitoring. Production needs chargeback mechanisms and detailed cost allocation to manage budgets. Every single line in this table represents work that someone didn't budget for when they approved the POC. So let me make this concrete with a pattern we see repeatedly in healthcare AI deployments. So month 1 to 3, a data scientist will build a POC that predicts patient readmission risk. And let's say they get 89% accuracy. They run it in the cloud for $5,000 a month. 2 people built it, and everyone is really excited about this. In month 4, legal gets involved. This needs HIPAA compliance. Patient data can't leave our data center. We need 99.9% uptime. Lives are at stake, and it needs to serve multiple hospitals, not just one. Suddenly, that $5,000 a month becomes a $200,000 a month estimate. The 3-month POC becomes an 18-month infrastructure project, and you need an enterprise infrastructure team, not 2 data scientists. So this composite example reflects common patterns that have been documented in healthcare AI implementations, where HIPAA compliance requirements, data sovereignty concerns, and production infrastructure needs emerged after the POC approval. And this is exactly how projects end up in that 87%. And then there's the cost shock. Let's talk about the cost reality, specifically GPUs. Training needs 8 to 32 GPUs running batch jobs for days or weeks. Inference needs 1 to 4 GPUs running continuously, responding in milliseconds. An NVIDIA A100, the workhorse GPU for AI, costs between $3.67 and $4.10 per hour on major cloud providers. AWS and Azure charge $4.10 per hour. Google Cloud is $3.67 per hour. Running 24/7, that's approximately $2,700 to $3,000 per GPU per month. So let's do the math for a typical production model. Training, 16 GPUs at $2,850 average is $45,600 per month. Inference serving, 4 GPUs at $2,850 is $11,400 per month. So for one model, you're paying $57,000 per month. Now, if you need to scale to 5 models, which is actually modest for an enterprise, you're now at $285,000 per month, which is $3.4 million a year. And this is the cost shock that kills projects. But there are infrastructure patterns that work. And that's the good news. So these are proven at AWS, Cisco, and enterprises that are running production AI today. Pattern number 1, hybrid cloud architecture. Use the cloud for training, so you need the burst capacity, but you can use on-prem for inference, which means you still meet compliance control costs, so you get the best of both worlds. Pattern number 2 is GPU pooling and multi-tenancy. Instead of giving each team dedicated GPUs that sit idle 80% of the time, create a shared pool. Multi-instance GPU, or MIG, on the NVIDIA A100s lets you divide one physical GPU into up to 7 independent instances. Each instance has dedicated memory and compute, and results from production deployments show that you can get from 20% utilization to 75% utilization. That's a 50 to 70% cost reduction, the same hardware and the same capabilities. And lastly, pattern number 3, model optimization. Quantization converts your model from 32-bit floating point to 8-bit integer precision. That's a 50 to 75% inference cost reduction and 4x faster performance. Most models don't need full precision for inference, so you get minimal accuracy loss. These aren't theoretical. These patterns have been proven in production and at scale. So what's the decision framework? So how do you decide? So here's a simple framework. Question 1, what are your non-negotiable constraints? If you're in healthcare, HIPAA might be non-negotiable. Data can't leave your control. If you're doing real-time fraud detection, latency might be non-negotiable. Sub 100 millisecond response time is mandatory. If you're a startup, cost ceiling is non-negotiable. You can't afford to spend $200,000 a month. Question 2, what's your risk tolerance? How much do you value data sovereignty versus convenience? Are you willing to build versus buy? Can you accept vendor lock-in for speed? And question 3, what does success look like in 6 months? And here's the key. Get your first production model running in 6 months, not the perfect platform in 18 months. You learn, iterate, and scale from there. The trap is spending 18 months building infrastructure before deploying model number 1. The third way is pragmatic hybrid. Use cloud where it makes sense, on-prem where required, and start small. Let me show you what this looks like by industry. So let's start with financial services. Banks and trading firms are running fraud detection, credit risk scoring, trading algorithms, and anti-money laundering monitoring. They typically choose a hybrid architecture. Cloud for training because they need burst capacity to retrain models on new data, but on-premises for inference. Why? Three reasons. First, SOX compliance requirements mean they need tight control. Second, latency is critical. When you're detecting fraud on a transaction, you can't wait for a round trip to the cloud. You need sub 50 millisecond response times. Third, cost control. When you're processing millions of transactions per day, those cloud API calls add up fast. Now contrast that with healthcare. Hospitals are building patient readmission risk prediction, medical image analysis for radiology, clinical decision support at the point of care, drug interaction checking. Their architecture is almost always on premises for everything. HIPAA compliance isn't negotiable. Patient data cannot leave their control. They must use cloud for research on de-identified data, but for production inference, that stays on-prem. Data sovereignty and audit requirements drive everything. Manufacturing looks different again. They're running predictive maintenance to prevent equipment failure before it happens. Quality defect detection on production lines, supply chain optimization, energy consumption optimization. This is true hybrid plus edge. On the factory floor, they need edge computing for real-time control. You can't wait for a cloud round trip when you're controlling a robotic arm. But they use cloud for training models on historical data and for analytics that don't need real-time response. And here's what's interesting. It's the same technology stack. Kubernetes, GPUs, ML pipelines. It's just deployed in completely different ways based on each industry's constraints. There's no perfect architecture. Each industry chooses their trade-offs deliberately based on what matters to them. And that's the real secret. The thing that separates successful projects from failed ones, there is no perfect architecture. There are only trade-offs that you choose deliberately based on your constraints, your risks, and your goals. The 87% who fail, they didn't choose. They let circumstances choose for them. They built a POC without thinking about production. They optimized for speed without thinking about compliance. They said yes without understanding the cost. And the 13% who succeeded, they made deliberate choices. They understood their constraints before the POC. They planned for production from day one. So that's the strategic foundation. Now, let's get technical. So for the next 30 minutes, we're going hands-on. So for practitioners, this is your section. Executives, stay with us. You'll understand what your teams are building and why these choices matter. So first of all, why Kubernetes for AI infrastructure? And there really are four reasons. First, container orchestration. Your models, your dependencies, your code, all packaged consistently using Docker containers. They deploy the same way in dev, staging, and production. There's no more, it works on my machine. Second, it's an abstraction layer. You write your code once, run it on AWS, Azure, Google Cloud, or on-premises. This is how you avoid vendor lock-in. Kubernetes is the portability layer. Third, it's built for scale. Auto-scaling when load increases, load balancing across instances, self-healing when containers crash, resource management for CPUs, GPUs, and memory. These are all capabilities you need for production AI systems. And fourth, it's the industry standard. There's a large ecosystem, strong community support, all the ML tools integrate with it, Kubeflow for pipelines, Kserve for model serving, MLflow for experiment tracking. So in short, Kubernetes gives you the infrastructure foundation that makes those hybrid, scalable, cost-efficient patterns we discussed possible. Let's cover the key Kubernetes concepts you need to understand for AI workloads. So nodes and node pools. These are the physical or virtual machines in your cluster. You'll have CPU node pools for general workloads and GPU node pools for training and inference. You can scale from 3 nodes for dev to 100 plus nodes for production. Pods and deployment. A pod is your container plus its resources. For AI, this is your model serving container. Deployments manage multiple replicas for redundancy and scaling. Services and ingress. These create endpoints for your models. Services handle load balancing across your pod replicas. Ingress provides external access. This is how your application calls your model. And persistent volumes, where you store models, training data, and shared artifacts. These are critical for AI because models are large, gigabytes to hundreds of gigabytes. These four concepts give you the building blocks for any AI infrastructure. And actually, next month, the presentation will be a deep dive specifically into these concepts and a hands-on workshop looking at how to bring up all this infrastructure that I'm talking about. So now let's talk about the expensive part, GPUs versus CPUs, and the decision that will make or break your budget. So for training, you have to use GPUs, period, unless you have very small models. Training on CPUs can take weeks instead of hours, and production models typically will need 8 to 32 GPUs for reasonable training time. For inference, it depends, and this is where you can save money. You use GPU inference when the models are large, over a gigabyte, real-time response is required, high throughput is needed, thousands of requests per second, or you need sub 100 millisecond latency. You use CPU inference when models are small, under about 100 megabytes, batch processing is acceptable, and cost is the primary concern, and requests are occasional and not constant. So here's the cost impact. For 1 million requests per day, GPU inference will cost about $36,000 per year, and CPU inference will cost about $3,600 per year. If you make the wrong choice, then you're wasting about $32,000 per year per model. And when you multiply that across multiple models, the waste adds up really quickly. So how does GPU scheduling actually work in Kubernetes? On the left here, you see a pod configuration that requests GPU resources. The key section is the resources section. And there you can see under requests, it's basically saying that I need 1 GPU to run. Under the limits section, it's basically stating that don't give me more than 1 GPU. The node selector field specifies the GPU type. So you might have different node pools, some with A100, some with older GPUs. This ensures you get the right hardware. And the tolerations field enables you to match up or line up with taints. So GPU nodes typically have taints, which prevent regular workloads from accidentally scheduling there. The tolerations say, I'm allowed to run on GPU nodes. Under the hood, this requires a couple of things. First of all, you need the NVIDIA GPU operator if we're working with NVIDIA hardware. It installs GPU drivers and container runtimes. You need a device plugin which exposes the GPUs as schedulable resources. Kubernetes treats GPUs as countable resources just like CPU and memory. So what about sharing GPUs? Can multiple workloads use the same GPU without interfering with each other? Well, they can through something called multi-instance GPU or MIG, which is implemented by NVIDIA hardware. So with a traditional approach, 1 GPU serves 1 workload. If that workload only uses 20% of the GPU, 80% sits idle. You're paying for capacity you're not using. With MIG on NVIDIA A100s, you can divide a single physical GPU into up to 7 independent instances. Each instance has dedicated memory and dedicated compute, and each can serve a different model or team. So for example, you could create different sized instances. So 3 small instances with 10 gigabytes of memory each could be on one card. Or you could divide it up into 2 medium instances with 20 gigabytes of memory each, or 2 large instances with 40 gigabytes of memory each. So the benefits are that your utilization can go from 20% to 70% average utilization. Your cost reduces commensurately from 50 to 70%. Using the same hardware, you're able to service more workloads. You still maintain isolation, so you have security boundaries between instances, which is critical for multi-tenancy. And there's still fairness implemented. The teams that share GPUs can share those GPUs without interfering with each other. And this is how you make expensive GPU hardware cost effective. Now let's look at the end-to-end ML workflow in Kubernetes, how all the pieces come together in the full pipeline. So in the first stage, you have data prep, and that's where you're extracting, transforming, and validating data, where you're doing feature engineering, and this will run as a Kubernetes job running on just regular CPU nodes. Stage two is training, and this is the expensive part. This is where you need a GPU cluster, and you do distributed training across multiple nodes, checkpoint saving, so that if a job crashes, it can be restored and continue running. And these all run as Kubernetes jobs on GPU nodes. Stage three is validation, where you're testing against your holdout data set. You have various metrics that you need to measure. You can A/B test against your current model. And this will be either using CPU or GPU, depending on the model size. Stage four is deployment. So this is model serving using Kserve. Kserve enables you to serve up a portfolio of models. It will automatically scale based on the load. Again, you can do A/B testing in production and do quick rollback if you need to, and these will run as Kubernetes deployments. And lastly, we have stage five, monitoring, whereas you look at the latency, accuracy drift, resource usage, and you trigger alerts if there are any issues. And this will feed back to stage one for retraining. So the key here is that all of these stages are running on the same Kubernetes cluster. It's the same infrastructure, the same tools, and the same deployment process. And this is the platform that makes your hybrid, cost-effective, scalable AI infrastructure possible. So what tools do we actually use to build these pipelines? So this is just a summary. The ML tools landscape is really huge. There are many tools out there. These are some of the most popular ones that are built on Kubernetes. So for pipelines and orchestration, you have Kubeflow for complete ML pipelines. There are Argo workflows for more flexible orchestration, Apache Airflow if we're already using it for your data pipelines. For model serving, Kserve is the Kubernetes native standard. And then you have the NVIDIA Triton for high performance serving and runtime, TorchServe for PyTorch models, TensorFlow for serving for TensorFlow. For experiment tracking, you have MLflow for experiment tracking and model registry. It also provides support for weights and biases for more advanced tracking. And then for monitoring, Prometheus and Grafana are the standard for metrics and dashboards, ElkStack for logs, and Datadog if you want a commercial provider. So all of these integrate with Kubernetes. And this is really the power of the ecosystem. You're not building from scratch, you're assembling proven components. So let's walk through and see what a real Kserve model deployment looks like. And this is how simple it can be. So this YAML file defines an inference service, and that's the Kserve abstraction for model serving. So key sections here, we've got the predictor, which specifies the framework. So in this case, we're using sklearn and where the model lives. In this case, it's Google Cloud Storage, but it could be S3, it could be Azure or on-prem storage. You've got the resources, so CPU and memory requests and limits. And notice that this is a small model. It's only got 100 millicore CPU and 1 gig of memory. No GPU is needed. And so what you get with this simple configuration, auto scaling. It will scale from 0 replicas when idle to n replicas under load. Canary deployments. You can roll out new versions to 10% of traffic, then 50%, then 100%. Model versioning. You can have multiple versions of a model living simultaneously. And monitoring. You can have built-in latency, throughput, and error tracking. This is production-grade model serving in less than 20 lines of configuration. I can't tell you how amazing the system is that provides this for you and makes it so easy for you to be able to access this. But a lot of work went on into the back end to enable this user interface. So the last technical topic for tonight, multi-tenancy patterns. How to safely share infrastructure across teams. So why multi-tenancy? So for one reason, cost efficiency. Shared infrastructure instead of per team clusters. It means your resource utilization goes up from 50% average, say, to 80%. You have centralized management, and so one platform team instead of multiple, and you have fair sharing of resources. Quotas prevent one team from monopolizing resources. And so the pattern we use here is namespace-based isolation. Each team gets their own Kubernetes namespace. You can think of it as a virtual cluster within the physical cluster. And here you can see we've got three teams, the marketing, finance, and research teams. The marketing team gets 4 GPUs and 32 CPUs quota. So they're running recommendation and sentiment models, and only the marketing team members have access via role-based access control. The finance team has 8 GPUs and 64 CPUs quota. So they're doing fraud detection and risk models and finance team access only. And the research team has 16 GPUs and 128 CPUs for experimental work. And again, only research team access. So quotas ensure fair sharing, RBAC ensures security, and network policies provide additional isolation. In addition to that, we have cost allocation, which is tracking which team uses what resources. And so let me show you what this configuration actually looks like in practice. And here again, we have Kubernetes manifests in YAML. So the first manifest is to create the namespace team finance. And this is the virtual cluster for the finance team. The second one is the resource quota, and this is the contract. So it puts hard limits on what this team can use. So 8 GPUs, 64 CPUs, 512 gigabytes of memory, and 100 pods maximum. And if you try to exceed these limits, Kubernetes will reject the request. And this will prevent one team from consuming all resources. And third, we have RBAC. And this role binding says, members of the finance team group have admin access within this namespace, but nowhere else. 3 configuration files will give you isolation, teams can't interfere with each other, fairness, resource quotas prevent hogging, security, RBAC ensures proper access control, and cost allocation. You can track usage by namespace for chargeback. And this is how you build a shared platform that serves multiple teams safely and efficiently. 2 more critical considerations for multi-tenancy: security and performance isolation. So for security isolation, network policies prevent cross-namespace traffic by default. Teams can only communicate with services you explicitly whitelist. Pod security policies prevent teams from running privileged containers that could escape isolation. You have secret management, where each namespace has its own secrets, so sensitive credentials are stored in external secret stores like HashiCorp Vault. You also have noisy neighbor prevention. So the resource limits are hard enforcement. It prevents one workload from consuming all CPU or memory on a node. Quality of service classes provide you and will enable guaranteed pods to get reserved resources, but you can also have burstable pods that can use extra capacity. So best effort pods use only leftovers. So this way you can guarantee that critical inference gets access and training jobs can get burstable access. With the use of GPU time slicing, that ensures also that you get fair scheduling, which prevents one job from monopolizing the GPU. So these patterns ensure that your multi-tenant platform is both secure and performant for all of your teams. The last piece of the multi-tenancy puzzle is cost allocation and chargeback. And so you need to track by namespace, by team. And so here in this table, you can see that we're tracking GPU hours consumed. So we can see the most expensive. We're tracking CPU hours consumed, storage used, network egress, and so on. And so you can see, just looking at that, how many GPU hours, the dollars, and the percent of the total costs that the finance, marketing, research teams are using. And so the total infrastructure cost is $70,224 in this particular month. And this is important because teams get to see their real cost. It encourages optimization, it enables chargeback to business units, and it justifies infrastructure investment to the CFO. And there are tools that you can use for this, like KubeCost and OpenCost, that are open source. Cloud providers have built-in tools if you're using managed Kubernetes. And with that, we are at part 3. So that's the technical deep dive. Now I'd love to open it up for your questions. There's been a lot here in terms of strategic decisions, infrastructure patterns, Kubernetes fundamentals, GPU allocation, ML pipelines, multi-tenancy. What questions do folks have? Happy to answer any questions you have. And by the way, if you don't have any questions, feel free to reach out to me offline as well. I'll bring up my contact details later on. But also would love to hear from practitioners, people that are actually doing this in production. Is this what you're seeing as well? Or what are you seeing that's different from this?
Hey, David, I just had a question about the use cases where you're talking about a hybrid approach is best. For example, training in the cloud and then doing inference on premises. So, what kinds of schedulers do you see out there? Do you see enterprises using two different schedulers? Once the model is trained, they take that model and pass it to the next scheduler for on premises? Or are there schedulers out there that unify the experience and maybe there's a flag for this is a training workload versus an inference workload, and then the workload is deployed to the appropriate underlying infrastructure?
That's a really great question. And so, in terms of schedulers, that's an area that I haven't looked into right now. What I'm looking at is just the basic schedulers or the standard schedulers that come in platforms like Kserve and Ray. So I'm curious though, have you had to deal with those custom schedulers or building your own schedulers for managing those types of scenarios?
Oh well, no. I'm looking for, I guess, somewhat of a holy grail. A one-stop shop that can just take my workload. Like once I put the data out to train, and I'm ready, and I'm done my testing, and I want to put into production, that'll put the model into production for me, and then I don't have to worry about that underlying moving around bit. But
Yep.
yeah, I'll keep my eyes open in the industry to see what folks come up with. I'm sure there's some open source project out there or something that's in the works.
I'm sure as well, and I'm also going to look into it, and I'll follow up offline with you as well, or I'll post it to the group discussion. That's a really interesting topic. I'm curious if there's anybody on the call that's had any experience with these types of schedulers.
I suppose so. I have not, but I would be definitely interested in the solution to that, as
Awesome.
I am just now starting a project that would be involving all of this. Uh, this happens right now. I've already trained on premise a medical image processing model,
Yep.
and so the next steps is fast API and Celery, right?
Got it.
To
Nice.
create the GPU workers, and then backend for web app and front end. So it's still
Yep.
creating the proof of concept MVP. And I posted here on the chat some of the options that I've seen. And one of them
Yep.
is RunPod in terms of serverless endpoint,
Yep.
which I had some questions, concerns there in terms of a cold start for serverless endpoint and how
Yep.
does it matter? I suppose in my case, I could do with batch processing since
Yep.
it's medical image processing. It's not
Yep.
live necessarily per se, or though you might want it faster, but and then I've also seen spot provisioning through fast vast.ai. If
Yep.
you familiar with it, essentially
I
people
am. Yeah, Vast
great
AI
awesome.
is great. I mean, well, great in the sense that they have a lot of GPU capacity, and it's a lot cheaper than the big cloud providers. I don't know about I don't know much about the company and how big it is, but from what I've seen, it looks very interesting for sure. The architecture that you were talking about, very familiar with that, and the serverless and thinking about time to first token. I mean, if you're doing interactive sessions, that's going to be a challenge because, especially if you have large models like with serverless. So there's a lot of strategies that you can use to work around that. But yeah, that's very interesting.
Thank you. Yeah, so right now, it's mostly light. It's segmentation models for medical imaging
Yep.
and classification models, etc. So just leaving the large language models for API, large language models APIs separate,
Yep.
which is a different cost, but it definitely saves a lot on things. So
Nice.
that seems to be the best budget uh, options, and I'm also considering based on existing incentives, like Google Cloud offers $300 for to start,
Yeah,
and I believe AWS and Microsoft might also have AI startup credits in the thousands
they do.
for an actual startup, not
They
like,
do.
yeah, not like a free
If
trial, but
Yeah,
a grant.
if you also get funded as a startup, I was talking to the AWS account manager at an AI conference a couple of weeks ago. They will give you thousands and thousands of dollars of credits if you can show them that you've been funded by a VC. So something to think about.
Oh,
Ve-
okay, so already funded.
Yeah,
Awesome.
yep, very good.
But
All right. Well, thank you for that, Brian. And thanks, Trevor, for the great question. Any other questions or comments? And by the way, I should also mention part of the reason why I wanted to start this group was so that we could, learn together and benefit from each other's experience. So would love to hear from more folks.
let's see everyone's question. Let's see this question.
All right.
So the one thing I didn't see in the slides
Yep.
is Terraform. So
Yep.
um, mostly goes over Kubernetes, which I see how it would definitely be useful for managing everything. But wouldn't Terraform be what would be scaling up everything?
It all depends. So usually for me, Terraform is to get your base infrastructure all up and running, and then on top of that, put your application. In this presentation, I'm considering Kubernetes as the abstraction layer. So you already assume Kubernetes is there somehow. You either are using managed EKS, GKE, or you have your own you have a distribution that you're running on your on-prem on your own hardware. But you're totally right. If you were doing all of this in the cloud and you wanted to use Terraform, you could totally use Terraform to manage the base infrastructure and then above. Yeah, so it's a good point.
Okay, right now I've been recommended Docker Compose to not get too crazy with Kubernetes and Terraform.
S-
Just
Uh,
but
so
and that's in terms of what to. So that's in terms of proof of concepts and pre-MVP and all that,
yep,
pre-production. But
totally.
then,
So
right,
Docker,
and
yeah,
go ahead.
Docker Compose is a great thing to start with. It's a lot simpler than Kubernetes. It's not really production grade. Kubernetes is where you go to when you want to go into production.
Right. So from Docker Compose to Kubernetes,
Yep,
essentially migration there.
yep,
Uh, cool. So I guess Terraform would be more of a hyperscaler if because essentially you'll be getting more provisioning that you might not need.
yep. Yeah,
Sure,
Doug,
sure.
yes, I'll make both the slides and the recording available. I'll send an email out. I have a few more to go through. So let me just go through those quickly.
The
It'll
more
kind of give
movies.
a preview of what's coming up next, and then we can wrap up. Alrighty, so let's see. Okay,
No
so here
comment.
are the four key
No
takeaways.
comment.
So first of all, enterprise AI is technically hard. Okay, I don't want you to think it's not hard. GPU orchestration, distributed training, model serving at scale, multi-tenancy, compliance integration. It's really complex infrastructure work. So don't let anyone tell you it's trivial. And I can tell you that from many years of managing this infrastructure. And I'm sure there are folks on the call who've managed or are managing similar systems that could say the same. But this is critical. It is solvable. Proven patterns exist, and we've gone through some of those patterns tonight. So, number two, despite the technical complexity, most failures are non technical, and 87% fail because of governance, compliance, and cost. And these are things that you can plan for. And so, the lesson there is Plan from day one. Don't say, we'll figure out compliance after the POC works. That's the path to the 87%. And then number 3, remember what we said earlier, there is no perfect architecture. There are only trade-offs that you choose deliberately based on your constraints, your risks, and your goals. The 87% who fail didn't choose, they let circumstances choose for them. And the 13% who succeeded, they made deliberate choices and planned for production from day one. And then the last thing I'll say is to start small, iterate, and scale. Get your first production model running in 6 months and don't shoot for the perfect platform in 18 months. Deploy one model, learn, optimize, scale, and Kubernetes provides the abstraction layer that makes this possible. So the technical challenges are real, but what kills 87% of projects isn't the technical difficulty, it really is the planning failure. And so now, so a bunch of resources for you. So next month, we're going to have a hands-on building production AI infrastructure with Kserve. So I'm going to walk you through 90-minute hands-on workshop where you'd be able to deploy a complete Kserve stack with GPU support. And so basically you'll be building what we discussed tonight. I'm going to publish this presentation as a blog post with a little bit more detail and also with references included there. I'll also provide some links to some of the key documentation for everything you need. There's a lot of information in here. So I'll give you references to NVIDIA GPU operator, the Kubernetes device plugins documentation, Kserve documentation. I have a Slack for ongoing technical discussions, and we can also use the discussion in the meetup group. And then I'll also put up my LinkedIn as well. So just to wrap up, so appreciate everybody coming tonight. Hopefully that was useful for you. Would love to hear if anybody is interested in presenting or has some topics that they would like to hear covered. And just remember that if you're dealing with these challenges, you're not alone. There are proven patterns there. Start small, iterate, scale. And I'll send the follow-up email tomorrow with the recording link, the slides, and the community links. And with that, that is it. So thanks very much, everybody. Appreciate it. Have a great night.
Yes, thank you, David.